It's lecture 6, fluid mechanics. Technically, Monday was lecture 5. So if you go to modules, it's going to go from lecture 4 to 6, because it's today. We didn't have class Monday. Okay? So today we're going to finish the rest of chapter 5, which is what you need for the rest of your homework. What is going on? That is weird. 1 second. Try that. What? It's not switching. Okay, is this okay with everyone? I'm just gonna leave it like that. Sorry, I don't know why that's not working. I think the guy said he switched something on here, and it could definitely just be me, so. Come on, mouse, make it back to my computer. Display, duplicate. Keep changes. Okay, all right, let's get started now. Sorry for the slow start. Okay, so we'll do announcements first. We already did quiz, so we're done with quiz, right? So announcements, right, Monday will be quiz. We already talked about that. Next Wednesday will be midterm. So I am planning on Monday, it's just gonna be me just kind of reviewing problems for your midterm, okay? So we're gonna have a quiz and then do review. So show up on time Monday. I might do the quiz in the beginning and then do review. I still haven't decided yet. And basically, it's gonna be everything that we learned up until now, which is write chapters 1, 2, 3, and 5. So homeworks 1 through 3. I'm gonna make a more elaborate list soon, and I'm gonna post that to you about what the midterm is gonna be on. So I'm planning, it's gonna, I don't know if you've had Dr. Bridge before. He kind of like lists out topics that you go through in class, and then he'll be like, out of these 5, I'm gonna pick 4 of these, okay? What to study, homeworks are good, quizzes are good, and like I said on Monday, I think I'm gonna provide some questions from the textbook that some of them I'll go over, the other ones I'll just say, hey, you study on your own. And I'm gonna try to post it as soon as I can so you can study early before Monday. Some of the questions might be pretty similar to the midterm. I'm gonna have 1 or 2 on there that you haven't seen, so it pushes you a little bit, right? But I don't wanna make it too tricky. I wanna give 3 points too. So whatever we review on Monday or I post, it'll be the exact same problems for that too. So that's what I'm thinking. I'll make a more descriptive announcement for midterms next Wednesday, but we're gonna review on Monday. Any questions about midterm? Yes?
What are we allowed to bring in?
Same thing that for quizzes, except you are allowed to, up to a full page of equations. And you need student ID, and that's about it. Same rules, right? Don't write any fully written out problems. I think that actually is makes it worse for you, because sometimes you're too distracted on the written problem and you won't get to actually look at the problem properly. And the reason why I asked for student IDs, I'm getting to know some names, but I don't know everybody. So I just like to I talked to a professor, right? They recommend you match the face to the exam or the quiz, in case the small chance in other college classes, they'll have other people take quizzes for them, which I don't think anyone will do here, but just to make sure, right? So yeah, calculators, I'm okay with anything, right? Just, you know, the honor system, right? I know some calculators can store data, things like that. So I don't want to be too picky. Just have a clear calculator. Anything is fine. Full sheet of equation sheet. And I think that's about it for what you can bring to midterms. Does that answer your question? Okay. Another question. I think this one here. Question for Sir?
Yeah, what's the time limit? Is it like an hour, hour and a half?
I'm shooting for 1 hour 20 minutes, or 1 hour to 30. And then for DRS students, we're going to use the rest of the time. And then, like I said, I don't even know the names of people here, a lot of them. But for DRS students, if you need more time than the 2 hours I'm giving, you can email me, and you can do a DRS appointment at their testing facility. But yeah, it's going to be around 1 hour 20 to 1 hour 30. Yes?
Are we providing any like constants like density or anything? Or you have to write it down?
It's a good question. I would recommend having some on your equation sheet. If you need it, obviously I'm going to solve the whole exam first myself. If you need it, I will have it on there for you. If someone asks it's great you guys ask questions during the quizzes. If you need it, I can also put it on the board. Usually if I don't, that usually is a hint that it cancels out. Then you don't need it. So, okay, answers your question? Okay, question over there?
Is that one page both sides or just one side?
One page both sides.
For the notes.
Oh, for the notes, yeah, let's do one page. I think front and back's too much. I think, yeah, right. I don't think I did that much content, so we'll do one. So we'll do one page. Okay. Any other questions? Okay. Right. Okay, good. Like I said, I want to make it less stressful for you guys and set you up for success. So I'll make an announcement, hopefully describing everything soon. But yeah. This important dates, quiz Monday, midterm next Wednesday. And then the next Monday, we're going to introduce a project. And this is a little different from the other section. I think they have 2 projects. I wanted to cut it down to 1. And they have other assignments for presenting, so I thought I'd just combine them all into one project. And hopefully I'm not too strict on grading the projects. It's more just for everyone to learn. I'll take feedback, but what I'm thinking is we're going to divide up into groups. And some of you are taking machine design right now, right? Is that true? You have like a really strict project of how to calculate things and things like that. I'm planning on not making it that descriptive. I'm making it something similar to like I took a composites class in grad school like a year ago, where we're gonna have like 7 to 8 groups, and then each group is gonna have a different topic of something that interests them for what we're learning in class applies to real world stuff. So, for example, maybe there'll be like a aerospace group. They're going to review Bernoulli's equation for an airfoil or a jet engine for a turbine. And then another group will be for pumps, right? And then each group will have their own topic. So everyone gets to learn from each other. I get to learn. And from math-wise and equation-wise, what I'm going to do is you're going to pick an equation of what we went through and how it applies to your topic. And then I'm going to have you vary like a variable, right? So let's say a fan diameter for a jet engine. If you increase the diameter, how does the efficiency of the engine be? Okay, so I'm thinking about having it pretty broad. I just want you guys to learn about something that you're interested in and learn from each other about real world applications, because you already have descriptive projects, and I thought this would be more fun. Yes?
Are we going to be given topics or we can choose?
I think I'll do a mix of both. Once I divide up the groups, I'll have maybe like 4 to 3 set topics, and then other people, depending on your group, you can pick one on the board that I'll have, and then you can pick one for your group as well. So a mix of both. Yes?
So is the deliverable going to be like a report on the topic or a presentation?
It's going to be a presentation. Nothing too stressful. It's going to be maybe like maximum no more than 10, 12 slides. It's going to be like, this is what we're researching, what it does. Here's the equation from class applicable to what we're researching. Here is the variable that we're varying and how it affects what we're researching. And then that's it. And then that way everyone gets to practice their presentation too, because I guess I've been working for like full-time maybe almost 4 years now. And one thing like in classes that we don't get as much experience in is presenting. So I thought that'd be pretty nice too. Did I answer your question? Yes, good. Okay, question?
Will you be splitting up the groups randomly or depending on interests?
That's a good question. I'll probably do depending on interests. That's a good point. I was gonna randomly assign groups just because it may be easier. So yeah, we'll have a class where we figure everything out for groups and interests. So I'll do interests on board and we'll brainstorm what do you guys want to do. And then we'll see raise of hands. Which ones do you want to do? And obviously there's a chance that you're not going to get what you want, but that's okay because you're still going to learn about it. And when we present, what I'm going to do, people are going to have like write something you learned about on other groups. So everyone's kind of paying attention and ask questions, things like that. It's good? Answer your question? Yes.
How large are the groups?
Sorry, what was that? Oh, I think we have about, last quiz, like 29 people took it. So, and some people missed, so we're around 32. So maybe I'll do groups of 4 to 5, something like that. Yeah, yes.
Maybe you could create like a poll or a form and take suggestions for the group, and then I think there's a way to put like titles on Canvas for groups, and then we could select whichever group.
Oh, okay. Thank you for the suggestion. I'll do that. I've done that before actually too, so I'll do that. I will probably do this after midterms though, because I don't want to stress you guys out about a project while you're preparing for an exam. If I forget to do that, remind me. Okay. Good? Any other? Yes?
It said that it might be online. When would you be telling us?
Oh, thanks for pointing that out. I'll make an announcement. I'm planning to make Monday's class in person. Depending what I prepare, if I don't think it's valuable, I'll just prepare some lecture videos of example problems I'll go through. Maybe one of them might be your midterm question, just like a little bit changed. And then I'll just do a really long office hours online for people who want to join. That way you get extra time to study. I'm leaning towards just coming here on Monday and just doing problems. But if I change my mind, I'll send an announcement. If I do have it online, the quiz 3 will also be on Canvas. And like I said, I am not making quiz 3 stressful because you have a midterm, so it's going to be one of your homework problems. So regardless, I think it'll be okay if that one's online. Good point. Thanks for pointing that out. Any other questions? Okay, think we are good. Let me try if I can go full screen one more time. It does not like it. Okay, I guess we're gonna have to deal with this. Okay, so now let's lecture and then hopefully get out of here early, I hope. Okay, so we're gonna talk about chapter 5. This was not a long derivation, it's just a quick example equation of the extended Bernoulli equation, and that's the last equation you need to solve the last 2 problems on your homework. I think last lecture you were able to solve problems 1 through 3. We're going to do an example, and then one more quick derivation. I think that's the last part of there's a part of the homework. You need another equation that I'm going to derive for that too. Okay? And then there's chapter 12, and I'm kind of looking at what section B is doing. They went through more examples, things like that. I'm just going to give you like a really conceptual intro of pumps and turbines. They call it turbo machines, which I think is really fun if you're into cars and other things like that. So I'm just going to talk about concepts. There's equations that you need for homework for that, so I'll put that in there. I saw the other lecture slides, they go into more examples, but that's not in your homework. I'm not going to put that on your exam, so I don't want to give you more content that you don't need for midterm next Wednesday. So this is kind of just going to be intro. When we learn more about it in the next future lectures, we'll go dive into equations. Okay, quiz is already done. Okay, good. Done too? Awesome. Sorry, do you have ID? Is anything? Roman. And I'll start to get better with names here. Roman, thank you, thanks. Okay, all quizzes are done. Sorry again for the hectic morning. I made it fair. Okay. Okay, so we're gonna get this equation in chapter 5 called the mechanical energy equation, and we're gonna derive it. It's basically starting off with Bernoulli's equation, and we're going to get it in terms basically of energy. So we're going to start off with Bernoulli equation, which you guys hopefully did on your quiz, I hope. So that's Bernoulli's equation. And what we're doing here is we're dividing each term just by density. So you see the rho is here and divided out. This cancels at the top, right? Specific weight. I have it in a different slide, right? But that's gravity times density. So this just divides all the terms by density. And then now, these terms, what they refer to, right? This one right here is kinetic energy per unit mass. This is pressure divided by density. This is potential energy per unit mass. So if you remember in your physics 1 class, you have your kinetic energy, 1/2 mv squared. You have your potential energy, mgh. I'm surprised you still remember that stuff. That's kind of these terms here in your energy balance. So you see from this step to this step, just dividing density, we have this new term labeled as loss. You'll see that, I think, in homework 3, problem 4. I have some slides that will deep dive further into what loss is, but that's basically your losses to friction. This is kind of loss explained in equation format. So this U hat, I'm going to call it, it's just internal energy per unit mass. I don't think we're going to do much of this U variable. I'm just showing you what loss is if you happen to need it. Okay? So internal energy out minus internal energy in minus Q net in. And Q net in is equal to this big Q dot. Right? Dot is just another notation for derivative. It's rate of heat transfer divided by mass flow. So this I wouldn't worry about too much. Most of the time it's just going to say loss on the equation. I just wanted to dive in what it means in variables. Okay? So now, I guess this whole slide, we're just dividing it by density. We got this equation from Bernoulli's, and then we're subtracting loss. We're going to call it also head loss. You'll see in a second here. Okay, so now we get to the equation that we want. It's the same as the previous, but now they're adding in this work shaft in. So that's essentially just most of the problems you're going to have in your homework, this is just going to be equal 0 because you don't have a shaft in there providing work for you. So most of the time it'll be 0, but this is the full equation you'll see in the textbook. Okay, but this will cancel out in your homework. So work shaft, it's your W dot shaft divided by your mass flow rate. And this is basically your net rate of work done into the system. So conceptually, that means if you have a turbine or something turning with a shaft that's providing power, that's going to be this. Okay? Loss, like I said, that's the energy that occurs in incompressible flow, meaning density does not change due to fluid flow friction. Right? So this is just your friction getting subtracted. Okay? I wrote some other equations that I was reading about for this work shaft. I don't think you'll need too much of this on your homework, but I'm saying I'm just providing them to you in case you need them. I would just write them down too just in case. So your W dot for the shaft is the torque of the shaft multiplied by the angular velocity. That's omega, that's W. Another way of thinking about this work done in the shaft is work shaft in minus work shaft out. And here we have efficiency. I have another slide for efficiency towards the end. That's what you're going to use for homework. That's going to be work shaft in subtracted by the loss, which is the friction, which is basically this term, right? Divided by your work shaft in. So you're basically having a ratio of the work putting into the system and then subtracting the friction of the loss. Okay, let's go down. Okay, so this is basically what you need for your homework. So it's in slides if you don't want to write it down. They refer to this in the textbook as the extended Bernoulli equation. and the units are units energy per unit mass, right? So energy, which is for work from your Physics 1 class. I hope it's the same, but Physics 1 was my favorite class because that's why hopefully you're in ME. Physics 1 should be your favorite. So right, work is Newton times meters, right? So that's your energy per unit mass is kilograms. If you do your dimensional analysis, you're going to get this meter squared over second squared. So, right, so a Newton, damn, this is not good. So you're going to be solving problems, and you're going to see my units are in meters squared over second squared. What does that even mean, right? So, right, so Newton is essentially kilogram times meters over second squared. Okay, so then you have times meter over kilogram. Okay, meters squared, second squared. Okay, this kilogram cancels. And this will be your units for one of your problems for the homework. Okay, I'm going over this in case I pick this problem for the quiz next Monday, right? I want you to really understand what it's about. So, okay, so we'll do an example problem of using that, and this will be the only example today. Then we'll have other concepts and we'll wrap it up. Do you guys need a break? Are we okay? We kind of took one during the quiz. We can get out of here early, hopefully, if we get through this quickly. Okay. Yeah, and if it's hard to see, I posted this. Hopefully you have that file. If you don't, let me know. Okay, so let's read this. A horizontal Venturi flow meter, which is essentially just this tube that has a narrow passageway here, consists of converging, diverging conduits as indicated in that figure. So the diameter of the cross section, there's cross section 1 here and cross section 2. And you see that there, right? D1 is 6 inches, D2 is 4 inches. The velocity and static pressure are uniform. You have your pressure difference between 1 and 2 here, which is your 3 psi. This should be rho. I kind of screenshotted this from the textbook, but that's your density of the oil. And yep, and loss per unit mass from 1 to 2 is negligibly small. So that means friction's not too applicable here. And it's asking you to determine the volume flow rate, right, which is Q. Similar, you had to use that Q in your quiz, right? Okay, so let's dive in. Let's see how far I can go. Do these recordings help? If not, I can stop doing them. Because if it's not helpful, it's okay.
Personally, I'd say they help.
Okay, awesome. Thank you. Okay. Okay, so let's do the full Dr. Bridge. Let's do our givens. Right? And then he's probably not going to watch my lectures, but I encourage you to do all of this when you do your homeworks. We're lucky we can be lazy. There's solutions, so you don't really have to. Okay, so let's list out givens. So D1, 6 inches, D2, 4 inches, rho, 56 pound mass over feet cubed. P1 minus P2 equals 3 psi. Okay, let's make sure we didn't miss anything. We have D1, D2, P1 minus P2, and rho. Okay. assume, we'll do it over here. I don't want to write out all the stuff I wrote on I did this yesterday. So I'm just going to put ideal flow here to be a little lazy. But that basically means, right, your flow is not turbulent, it's not going crazy, it's nice and steady. Your density is the same. When you measure parameters at specific locations, you're going to have the same value, right? So it's non-viscous, incompressible. I'll write that down. Okay. And then they also said stuff on there. You could write that in the assumptions if you want. They said loss per unit mass from 1 to 2 is negligibly small. They also said velocity and static pressure are uniformly distributed. So you can put that on there too if you'd like. Save us time, I won't write that all down. Okay, we talked about our assumptions. Okay, find, what are we finding? We're finding Q. Someone want to tell me the only equation we have for Q? Yes, thank you. AV. I like AV. It's easier for me to remember. One of my smaller dogs is named AV. So, okay, Q equals AV. So hope you used that for your quiz. That was the last step you needed for after you got your answer from velocity. So, okay, let's do it. Solution. Any questions so far? No questions. Okay, we're going to write our energy equation that I just derived for us in slides. So let's do this quickly. P2 rho plus V2 squared divided by 2 plus G Z2 equals P1 over rho. 2. Okay. So, like I said, the full equation has this work shaft. We don't have a shaft here, so that's 0. Okay? You'll see in my other slides too, and that's also work being put into your system. Okay? We assume this loss, right, from an assumption, this is going to be 0 as well, right? Because we're assuming friction is negligible or 0. So that's 0. Anything else stands out that should be 0 that we might not have?
There's no change in height.
Thank you. A change in height. That's another thing, right, when you take in midterms or quizzes. If you don't have something, where can I get it from? There's no linking equations. You can probably assume it's 0. When it comes to the midterm, you can ask me about that too. Yes?
So W shaft is 0 because there's no friction?
W shaft is work being put into your system. So, for example, maybe there is a shaft turning like a turbine and adding more energy flow of the water moving faster. So that's work going in. Loss is work coming out. That's friction.
Okay, gotcha.
Okay, good so far? Okay. All right, so now let's write what we have. So we have P2 rho plus V2 squared 2 equals P1 rho equals V1 squared 2. Okay. Okay. And we basically are trying to work to get Q. So you're probably solving this, you look at this, where the heck is my Q, right? So that's going to be here. So we can work on the side here if Q1 equals Q2 A1 A1 V1 equals A2 V2, right? Continuity equation. Said in quiz, we couldn't assume that in our quiz, right? Yeah.
So just why are there two equal signs in the?
Oh, sorry. I don't know why this line threw me off. It's impossible, right? Why is that there? Thank you.
Well, it is possible.
Oh, it is possible, yeah. Right, but that equation wouldn't work. Okay. Okay, so let's solve for V1, right? So V1 is equal to Q. All Q's are the same, so I'm just going to make this Q1, Q2 is equal to Q. Okay, so V1 is equal to Q over A1. V2 is equal to Q over A2. Why am I doing this? Because I'm going to plug these guys into here. That's why. Sorry for people in the back, but I will leave this up and you can take pictures of them. I'll write it over here so you guys can see. That's Q over A1. Okay. Okay, now we solve. I'm just gonna kind of plug in as we go and get an answer. I'm not gonna waste too much time plugging in the values because you guys can do that. So let's plug in. Okay, let's leave this here. So P2 over rho plus V2 squared. So that's going to be Q squared over A2 squared. So V1 A1 squared. Okay, let's make sure that's right. We just did feed 2, plug in Q squared, A2 squared 2, P2, V1 is V1Q, A1 squared, bless you. Okay, looks good, just plug that in. So you guys see the kind of the repetition, right? If you're gonna be missing something here, where do you go? Continuity equation. Small chance you might use ideal gas law if you're dealing with gases, if you're missing variables. Okay. So now I'm going to combine like terms from one side to the other. I'm going to have this P1 and P2 on the same side, so it's P1 minus P2, so I match this 3P aside there. So it's going to look like this. Do it here. So we're going to have Q squared over 2A2 squared minus you guys probably already starting to see it, right? But we're basically just solving for Q. So I'm going to skip some steps in my head, but basically I'm going to factor out this Q, divide this whole term to that side, square root. I don't know if it's the same for you guys, but once I started like getting to my junior year, algebra became pretty fast, right? When you're doing your math problems, you already see this, the way to it, so. Okay, so do Q is equal to we'll make this neater. We can take out the row on the outside. Okay, factor that row. Gonna divide this whole term by 1/2. Squared. Okay, let me check my math. Factor out the row, P1, P2. Factor out the Q. 1/2, 1A2 squared, A1 squared. Good. Okay. A pi r squared pi. So this is the area. I could put it in, but I think it'll be messier, right? So I'm not going to do that. Okay, does that look good? No mistakes?
I got the same thing.
Awesome. So we'll save time. I will not plug it in. I have the answer. I will not make you plug it in. Okay. Any questions? Yes.
Couldn't we just use the old equation to solve this problem?
Let's see. Yeah, I believe so. The only difference is we're putting in that. That's a good point. You can. This was the original Bernoulli's equation. It's a little different because you take out the density, but that doesn't matter too much. So yes, you can, because we assume these are 0. If we assume these are not 0, you need the new one that we derived. Yeah, but good point. Yes.
So I solved it on my own, and I can't figure out where to get the seconds from. Because there's PSI for the pressure. We have density, pound per feet, and the diameter, which is only inches. And I can't figure out where to get the seconds from.
I'm pretty sure the density is pound mass. So you have to do some sort of comparison to get your
Density upon mass.
Okay.
I'm not entirely sure what it is.
Right. So let's see. We have pressure, density, area. Can you repeat that one more time, Carlos?
I'm pretty sure that PSI is in, or density is in pound mass, and your PSI is in pound force. So there has to be some sort of conversion factor. It's like 32 something.
Through gravity?
Yes,
Some sort of.
I'll have to look into that, but that's a good point because it's just scratch work. Yeah, let's try to see if we can find it. N over meters squared, that's that. 1 over rho is density, so that's meters cubed kilograms.
Doesn't Newton's already have acceleration in it somewhere?
Yeah, that's it. Yeah, thanks. That's where your second should come from. I can keep working it out, but yeah, that should where it comes from. You guys, let's see, we'll see. One area. This is going to be. Oh, we're working in feet. I'm just going to do an SI units just because we already have it up here. This is going to be meters squared, but that's going to go back to the numerator. Squared. Square rooted. Okay, let's see if we can find it. Aha. Okay, so in SI units, this is all square rooted. This is just me thinking. So basically things will cancel out. But this second squared at the bottom is square rooted, so you get to seconds. This is SI units. But I think in their English units, should be something similar because you're going to have a force. So did I answer your question? Whoever asked, that was a good question. So yeah, you're going to get something with acceleration. This whole term is square rooted, so that second squared on the bottom will get to seconds if you work it out. Good question. That's why I love units, right? If things doesn't make sense, they'll show in the units. Okay, any other questions? We're good? Okay. I will erase this dimensional analysis I did, just so when I take a picture, it doesn't confuse people. If you do find a conversion for that, let me know. If there's something from pound mass. I think in one of my slides, I had a conversion from slugs to pound mass. And I think it's multiplying by 32.2. And that might be lecture 1. So I would double check there. Okay, let's get through the rest of this lecture and we can call it today. Okay, did the problem. Okay, we have one more equation here, and this is another one you're going to need for the homework. Basically, if you multiply all of these terms by density again, this is why I don't really like the textbook. When they derive stuff, they go back and forward. Say, okay, we'll divide density for one step. This is your equation. We'll put it back in for the next equation. So I'm just following it. So you multiply all of these by density, you get this, and you have specific weight is rho times gravity. And then you divide all the terms by gravity, and you get this. Right, still kind of looks like Bernoulli's equation. I will explain in the next slide what this H subscript S and H subscript L is. It's basically exactly like the last equation, but this is energy per unit weight, just different units. If you do the dimensional analysis, it just becomes a dimension too. And I'll explain that in a second. Okay, so HS stands for shaft work head, and HL stands for head loss. So you see in our previous equation, right, that was like the work shaft that we had. This is just changing the units. So the term head is energy per unit weight. So they'll ask you, what is this head term, right? It's essentially if you have your energy, which is your force times distance, divided by another weight, which is another force. You just get meters. So I don't know if anyone will go into like a fluids job, but they're going to say, oh, what is your head loss? It's basically your friction loss in terms of energy per unit weight. Or what is your shaft work head, HS? That's what's energy is going into the equation. Same units, right? Yeah, so you can see exactly the same equation as before. The two terms just got this HS and HL, and this is what they are. And I found some more deriving if you need these terms. You'll see in your homework that you'll kind of get HS and HL from your equation here. But, right, so shaft work head is just your work shaft net in divided by gravity. And that makes sense because, right, you have this units of head, which is just meters. Okay, work shaft in divided by mass flow rate times gravity. You can sub in your Q. That's the shaft work head there. Head loss, it's that loss term, which we defined earlier, right, with that whole internal energy U hat thing, divided by gravity. Yeah, I'm starting to notice too, like whoever pointed out in the back, a lot of these equations look pretty the same, right? It's just changing units. So, okay, and on each slide I define every unit so it's not confusing. So, okay, questions? Okay, so here I found more equations for the total head, which is essentially your pressure divided by specific weight. And it's basically the one term, one side of your Bernoulli's equation, right? V squared divided by 2g plus z. You can have your total head out equals your head in minus these two terms, right? Which is the shaft work in minus the HL. So you could think about it as, total head in and out minus extra head put in minus the friction. And this is kind of a good thing to notice. You'll see in your homework the sign convention might change. Or change when you're doing your equation from what I derived earlier. HS is positive for a pump and negative for a turbine. Why? Because a pump is putting in work, right, into your system. A turbine, which I'll explain later, is it's using fluid to provide movement, so it's taking work out. And we're going to go over pumps and turbines in a second here. Okay, any questions? We're going to go into chapter 12. I think this is fun stuff. It's just we're going to talk about concepts, and then we're going to be out of here. You should now have almost everything you need to solve the homework. I have a last few equations near the bottom here, and then we should be good. Any questions before we dive into chapter 12? Okay. So, I guess the way I wanted to show this to you, this is kind of not be exactly your project, but it's going to be similar. Like you're going to find something that interests you, and then how it applies to the class, and then you're going to present it. So this interests me too, obviously, but this is literally in your textbook too. So chapter 12 is about turbo machines, and this is like my definition of how I understand turbo machines instead of finding some textbook definition. It's a machine that transfers energy due to flowing fluids causing components such as a shaft or rotor to rotate. So think of a fluid like water rotating some kind of component, and you use that energy to either provide power or some kind of output. Okay, so examples of a turbo machine that we're going to look at is mainly pumps and turbines. And what I listed here is the big concept to it, right? So pumps, it does work and adds energy to your system. So if we have a Bernoulli problem and a pump is pumping in water, you're adding energy in, right? Turbines extract energy from a fluid. You have loss of work on turbine. So here's an example, right? You have your normal pump you put in your air mattress. That's an air coming in. We're going to talk about a turbocharger in a car. So that's pretty cool. This little meme, I'm kind of into cars. Can anyone tell me what car this is? Right, it's a Supra. Right, yeah, it's a Supra. They have a 2 JZ engine. I hope you know who Jay-Z is. That's just like a little joke. This has a twin turbo setup. Twin turbos are more complicated. So we're just going to talk about a single turbo. I just thought it'd be funny to put in there. Okay, and I think one of the topics that we could have is something with turbochargers, because this is literally a turbine. So this could be one of the topics that one of your groups do if you're interested, right? So like I said, maybe you'll do something, if I vary the airflow, if I increase it, how much more power do I get? How much more turbo boost do I get? So that could be a fun thing to learn about, right? Okay, so how a turbocharger works, explained. So this is housed into this. It's a little fancy because there's just an inlet and an outlet, but these rotating components are right here, right? So essentially, for like a big rundown of how cars work, right? If you have more oxygen cooling off your engine when it's firing off the pistons and cylinders, you get more power because your engine's running more efficiently. So the whole point of a turbocharger is to, and it's kind of interesting, right? Because you always hear people, I put a turbocharger on my car and made it a lot faster. They're basically putting a system that adds more air and high denser air that cools off your engine, and that makes it more power. Okay? So how this works is, you know the exhaust from your car, right? That it comes out. It will essentially use that exhaust to rotate this turbine rotor, which is, these are called vanes sometimes, and we use that exhaust to basically rotate this. And then once that's rotating, that will turn this shaft, and it will turn this compressor. And then this is sucking cold, fresh air in, right? And you'll see in a video, that fresh air will somehow make it back to your engine. It goes through an intercooler first to cool down the air. So again, use the exhaust from your car, that's the bad air, rotates this. Once this rotates the shaft, rotates the compressor, gets fresh air, and that goes into your engine. This is a really good video that I found.
Works.
Let's just skip through it. So here, your exhaust comes in, like I said, right? And that exhaust is, I don't have the exact numbers, rotating really fast, and it causes one of that rotors to rotate. That causes this shaft to rotate, 280,000 RPM, that is a lot. Okay, so once this is rotating, you have your compressor, which is now rotating, getting fresh air from the outside air. That's that blue arrows you see there, ambient air. And this dense air, it goes through this air cooler. So I don't know if you talk about it in thermal, but you talk about it in maybe heat transfer. We want the air to be cooler now, so sometimes this has a fan, so when that air is coming in through tubes, it'll cool off the air even more. So now you have high density air. This is where the money's at. So let's freeze it right there. Now cold air is coming back to your engine, right? So this is just coming up and down your piston. I don't want to get into car stuff, but right, you have your normal gas coming in, the spark plug ignites the piston, goes up and down just like this. So this is providing more clean air, so then your strokes are a lot stronger. And that's kind of how a turbocharger works in your vehicle. We'll not get into V6s or anything. Any questions on that? That was kind of cool. So now when people install it, you kind of know how to have an idea what it is. In a nutshell, it's adding more high dense air to your engine, and your pistons providing more power. And then, I guess just to even go more depth, because I find this stuff interesting. This piston's right, it will rotate another shaft down here. There's a big shaft system that connects to your wheels, basically. So as this rotates, a bunch of shafts and gear ratios rotate, and that is how your wheels rotate on your car. As this is going up and down, this is rotating a shaft, a bunch of gears and shafts rotates your wheels. So that's why if this piston is going more efficiently with that air, that's why your car is going faster. Okay? And here, anyone know what this car is? Oh, yep, Skyline. That's one of my dream cars. So you can, I'll turn this up. You'll hear a little turbo spool. Ooh, too loud, too loud. So if you hear that turbo spool sound, that's the compressor. So that sound is literally just a whistle through the compressor portion, right here, right? So once you take off your foot off the throttle, right, that compressor air needs to go somewhere. So that's why you hear that little whistle going through these vanes, that compressed air. Okay, and now just a quick explanation of a pump. This is what they call a centrifugal pump. I don't know if you guys use centrifuges in your chemistry lab. Basically, if you have something rotating, right, you have centripetal force. I think that's m over v squared, something like that. I had it in a different slide. But as this rotates, water goes to the edges. So you have your impeller here, which is essentially just like a wheel, like a water wheel, but it's designed so you can house water better. And once the water's in here, it'll rotate, the water comes out, it touches this housing, and then discharges out there. That's how a water pump works. Yeah. And this video will probably show it better. Just 20 seconds here. So water comes in, right? It's just spinning that, and that centrifugal force is going onto the housing, causing it to rotate outwards. So another project could be a pump, right? If that's interesting to you. And here are some efficiency equations for pumps and turbines. I believe you need this for your homework. I think for one question. If not, we'll use this in the future. But this P subscript, this is still your head, right? So your P and your T, that just stands for pump and turbine. And we already defined HS earlier, right? And right, efficiency is basically just showing your power in divided, or your power in loss with your loss added with friction divided by the, actual work. So then that's how efficient your system's functioning. Okay. Okay, that's all I got. Is there any questions before we end class? I'll have little office hours if you want to talk about anything. Quiz was okay today. Hopefully I made it not too bad. Like I said, it was literally last week's example problem. I just changed the variables. So hopefully we did better on that. Other than that, thanks for joining me today. I'll make an announcement on Monday what I decide if we're going to have class or not. But we're going to review for midterm, basically.
So what's the best way to study for the midterm? Just go over the homeworks, or do you think I would need to?
Yeah, homeworks are... Yeah, being able to solve the homeworks are good, the homework quizzes. And then the list of example problems I'll provide will probably be the best thing to study. Which I still need to do because I haven't written it yet. So.
What card do you have?
Oh, yeah.